Greetings and welcome to the Containers, Kubernetes Cluster, and Nested Hyper-V Virtualization Lab. In this lab, we will stand up Kubernetes clusters to serve up websites. The lab will feature two different kinds of Kubernetes cluster configurations. One Kubernetes cluster will use Windows Server for worker nodes to serve up an IIS web page. The other Kubernetes cluster will use Linux worker nodes to serve up an Nginx website. After standing up the Kubernetes clusters, we'll configure our Hyper-V host for nested virtualization. Then we'll create some demo nested virtual machines inside of our nested virtualization host. On my GitHub site, I've made some supporting files to build the Kubernetes clusters and to set up nested virtualization. They're located in the 26S-AZ800-labs repository. And I have these two folders, one called Docker-micro K8s to run IIS_custom image from Dockerfile. And then the next folder is K8s to serve custom Nginx website. So the word Kubernetes begins with K and ends with S. And there are 8 letters in between K and S. So that's how they get the abbreviation K8s. So you'll hear me use K8s to refer to Kubernetes. So we'll begin the video with a high-level overview, and then we'll look at the code, and then we will execute the code and configure the lab. So a good place to begin the discussion is talking about modern processors. So modern processors have user mode and kernel mode, and this is one of the most fundamental concepts and how modern processors and operating systems work. So in this diagram, we can see we've got our kernel mode and our user mode. Now I've got a little chart that just highlights some of the differences. So kernel mode has full access to privileges, memory access, all memory, hardware access direct, instructions all, runs kernel plus driver, crash impact is system-wide, performance is faster. And then when we look at the user mode, when we look at privileges are highly restricted, memory access, own memory space only, hardware access via the kernel, instruction, safe instructions only, runs applications, crash impact, program only. So this is just a little chart just to highlight some of the differences between these two modes that modern processors have. So the kernel mode and the user mode. So the top layer, the red mode, the kernel mode, contains the kernel plus the core operating system components plus drivers. It has direct hardware control. The bottom layer, which is the blue layer, is called user mode, where all normal applications run. They cannot directly touch the hardware. So how this works in practice is applications will run in user mode. They're sandboxed for safety. When an app needs something privileged, like open a file or send network data, or like allocate memory, it makes a system call. When we say system call, we mean the CPU switches from user mode to kernel mode. The kernel performs the requested operation, then switches back to user mode and returns control to the application. This switching is very fast, but it still has a cost, and that's why syscalls are not completely free. So the CPU is very relevant when we're talking about technologies like Docker and Containerd, which are container technologies. So containers run in user mode just like regular applications. So they share the host kernel and they don't have their own kernel. The kernel uses several technologies to isolate containers while still running them in user mode, like namespaces, for example, separate views of processes, network file systems. So the key point here is even though containers feel isolated, they still share the same kernel in kernel mode. A kernel vulnerability or container escape can potentially affect an entire host, unlike virtual machines which have their own independent kernel. So in summary, kernel mode is kind of like a God mode. The operating system has full power, high risk, right? User mode is like a sandbox mode. Applications are restricted, much safer. So containers use this advanced sandboxing inside user mode using kernel features, but still sharing the kernel. So Hyper-V is Microsoft's native Type 1 hypervisor. Type 1 hypervisors are also called bare metal hypervisors, and they run directly on the physical hardware below the host operating system. So how it works is the hardware layer is on the bottom. The physical processor must support virtualization extensions. The big ones are VT-X and AMD-V. So these extensions allow the CPU to efficiently run multiple operating systems at near native speed. So the level 0, this is the core hypervisor. It sits directly above the hardware and has the highest privilege. It controls the physical CPU and creates virtual CPUs for each virtual machine. It manages memory isolation, device access, and scheduling between the hosts and all guests. So then we need to talk about level 1. So when you install Hyper-V on Windows 11 or Windows Server, the Hyper-V hypervisor loads first. The normal Windows OS, what you see as your desktop, is then turned into a special virtual machine called the root partition or the parent partition. And in this this is why the host OS runs at level 1, not at level 0. And so this right here, this Windows root directory, this is our level 1. And then we have our guest operating system. So each virtual machine you create runs in its own guest OS kernel. The guest believes it's running directly on hardware, but it's actually running on the virtual hardware provided by Hyper-V. And then we can see the guest operating system here sits on top of the hypervisor in this diagram. So the connection to user mode versus kernel mode has to deal with what's going on inside the host, the Windows host. The host kernel runs in kernel mode, and your applications run in user mode. So inside each guest VM, the guest OS kernel runs in kernel mode from the guest perspective. And then the guest applications run in user mode. So now we'll do a side-by-side comparison of containers versus virtual machines. So on the left here in green is virtual machine, on the right is containers. Each virtual machine is completely independent. Every VM has its own guest OS, which includes its own kernel. This is like having multiple separate houses, each with its own plumbing, electricity, and foundation. Hyper-V sits underneath and manages them all. So on the right side is containers. So all containers share the same host operating system and the same kernel. They only contain the application plus its dependencies like binaries and libraries. This is like apartments in the same building. They share the foundation, the plumbing, and the electricity, which you could refer to as the kernel, but each apartment is isolated from the others. So the container engine, like Containerd or Dockerd, manages the containers on top of the shared kernel. So why does the shared kernel matter? And it all comes down to efficiency. So no need to load multiple kernels, which is a massive reduction in memory and CPU usage. When we talk about performance, containers start almost instantly because they don't have to boot a full operating system. We can also mention density. So you can run far more containers than virtual machines on the same hardware. And we'll prove that in our lab environment here shortly. So there are some trade-offs. Containers have weaker isolation than virtual machines because they share that kernel. A kernel vulnerability can affect all containers on the host. This is why proper security configuration and namespaces are important. So this diagram illustrates how containers work on Windows Server using containerization or Dockerfile as the runtime, which is this middle layer. So the top layer is the user inputs, like Docker CLI, Kubernetes. The middle layer is the container runtimes, so containerd, Dockerd. And everything ultimately sits on top of the Windows kernel. So Windows uses several services to support containers. HCS v1, which is host compute service. And there's also a HCS v2, and this creates and manages container sandboxes. And then we have the HNS, which is the host network service, and that manages networking for the containers. So the key takeaway is even though Kubernetes and containerization are Linux-style tools, on Windows they rely on Microsoft's host compute service and the Windows kernel to run those containers. This is why we will install the containers feature plus containerization on our Windows worker nodes, and this bridges Kubernetes with the Windows kernel. So now we'll move on to an interesting topic, and it's process isolation versus Hyper-V isolation. So in this illustration, on the left side we have process isolation, and on the right side we have Hyper-V isolation, and this is for containers. So we'll discuss the process isolation first here on the left. So this is also just called Windows Server Containers. It's the default mode. Lightweight, high performance, containers share the same kernel as the host. And that's what we can see in the diagram here is we have our two containers and they're sharing the host kernel of the host operating system. So on the right, we have Hyper-V isolation, also called Hyper-V containers. So they have stronger isolation and higher security. Each container runs its own lightweight virtual machine with its own kernel. So a common misconception here is that there are two hypervisors, but you can see there is just one hypervisor. Hyper-V isolation means that the server will virtualize a lightweight virtual machine that then gives us our own kernel, and the container runs off of that kernel. So that is what we mean when we say Hyper-V isolation or a Hyper-V container. So this is the same diagram as before when we first looked at how virtualization works, but instead of a full-on guest operating system, we just run a very lightweight guest virtual machine that just virtualizes the kernel essentially for us. So the concept here is that our container is running in a lightweight virtual machine when it is Hyper-V isolated, and when you're using process isolation, it's using the host's kernel. So I do have a little diagram here to show some of the differences. So we'll talk about containers, and then we'll talk about the Hyper-V containers. So normal containers process isolation is low to medium. Isolation level, they share the host kernel. The kernel is shared with the host. Security is good, but you share the kernel. Performance is near native, so it's very fast. Resource usage, very efficient. Use case development like this, testing and trusted apps. So when we look at the Hyper-V containers, process isolation is high, maximum. So isolation level, each VM has its own kernel. The kernel is independent kernel per VM. Security, excellent. So kernel level isolation. Performance, slightly slower, but still pretty good. Still very good. Resource usage uses more resources. Each has its own operating system, its own lightweight virtual machine. Use cases, production, and untrusted code, high security. So those are just some different cases where you would use one type of container over the other. So on the left, the goal is efficiency and near-native performance. The goal on the right is maximum security and strong isolation. So we're now ready to move on to discussing Kubernetes clusters. Kubernetes is an open source container orchestration platform. Orchestration means Kubernetes will automate the deployment, scaling, scheduling, networking, and management of the containers across multiple nodes. So this diagram is a representation of how orchestration works. So the administrator sends instructions to the API server. The control plane node, also known as the master node, in this diagram it's the cluster master, decides where and how to run your containers. So this is the scheduling part of orchestration. The control plane node then sends instructions to the kubelet on the appropriate node. The kubelet works with the container runtime to start and manage the containers. Kubernetes is called a container orchestrator because it automates and coordinates everything needed to run the containers reliably at scale. So this entire technology is known as Kubernetes. So this is another representation of a Kubernetes cluster. So we'll have a Linux control plane node, and then we'll have our 4 Windows worker nodes, and then these are different variations of how the containers can be set up in their pods. So we need to talk about 3 terms real quick: node, pod, container. So we'll just start talking about the container. This is the smallest unit of packaging for your application. A container includes your code, runtime, libraries, and dependencies all packaged together, so it runs consistently anywhere. So the best practice with containers is they should be scheduled together in the same pod. They should only be scheduled together in the same pod if they are tightly coupled and need to share a resource like a disk or network or a namespace. Most applications run with just one container per pod. And so that would be an example of these 2 nodes here. So we have 2 nodes and then 2 pods, and those pods just have one container. But it is possible to have a pod with 2 containers because they need to share like a volume. So, and even though it's possible in special use cases, what the curriculum teaches is that most cases that you want to use, you'll just want to use one pod. So now we'll move on to talk about what the pod is. So the smallest deployable unit in Kubernetes. So a pod can hold 1 or more containers. It represents a single instance of an application or a small set of related processes. So you define pods using templates inside controllers like deployments. And that's what we'll be doing. We'll be doing a deployment. So you define pods using pod templates, like I just mentioned, and those will specify the container images, the ports, the environment variables, resource, request limits. and volumes and other configurations. And then probably the simpler term to understand is nodes. These are the actual Windows server, the actual servers. So the worker machines in a Kubernetes cluster. The node can host multiple pods. They can either be a virtual machine or a physical machine. So in our lab demonstration, we'll be using virtual machines. And so each node is managed by the kubelet, which is the agent running on it, which then communicates with the control plane node. And this does stuff like start and stop the containers via the container runtime. So this is just getting us more familiar with what the Kubernetes cluster is and what we're trying to achieve. And then what we'll do in the lab is each container will be an instance of either IIS for the Windows Server nodes or Nginx for the Linux nodes, and then each pod will serve up our custom website. So, we'll only have 4 worker nodes, but we'll actually be able to have 20 instances of IIS, for example, in the first lab, demonstrating the efficiency of the containers. So after we finish up the Kubernetes clusters, I just have a short lab about Hyper-V nesting and how to set it up. So Hyper-V nesting is also called nested virtualization, and it allows you to run a hypervisor inside a virtual machine. So this means you can create VMs inside of other VMs. And so this is very useful for labs, testing, training, and running container platforms like Kubernetes that need the virtualization support. So this diagram shows 3 different layers. So the level 0 is the hardware and the hypervisor layer. Level 1 is the Windows kernel and the root directory. And then level 2 is the nested Hyper-V hypervisor in the guest OS. So that's just a bit of the terminology that's used when we start talking about nested virtualization. If someone says level 2, they're referring to the hypervisor within the other hypervisor. So virtualization extensions must be enabled at every level, so the inner hypervisor can talk to the virtual CPU. So the host Windows kernel level 1 runs a nested Windows kernel level 2. So you can see the virtual CPU being passed down through the layers. And so this is really neat. So we've got our original hypervisor that we talked about earlier, and this brown section was just a guest operating system, right? So now we've taken a virtual machine, enabled the Hyper-V role on that virtual machine, and now we have another hypervisor. So we'll come back at the end of the lab, and then we'll stand up some of these nested virtual machines. So we'll use a Dockerfile to build a custom container image that we'll use for our IIS image that then we will use to push to the pods to make our website. So the way that this works is we create a Dockerfile, and so we add instructions to that Dockerfile that then builds the Dockerfile, and then we can run the image to create containers whenever we want. And so I've got a simple example here. So these are some of the instructions that we'll use in our Dockerfile, and in just a moment we'll take a look at the lab Dockerfile. But for example, the from instruction allows you to start from a base image. So for example, we'll pull down the Nano Server Core 2025 image, and then we'll use that as our base image for our custom image. So it gives you a starting point, gives you all the dependencies and libraries that you might need. For example, we could use Server Core, but it's not going to have IIS installed. So if we use the IIS image that's also available on Microsoft, when we see in the demonstration that it will have the IIS role, and we can just begin configuration without having to install that role. So this is just a short example. So that in this example, from node 20 Alpine, that's the Alpine Linux image, we're going to create this work directory that's an app. We're going to copy this JSON file, install some dependencies, copy more custom code, expose a port, and then define a command to run when the container starts. So all of that will be defined in the file, and then we use the docker build command to then execute that instruction set against our base image and whatever else we want in our image, and then we'll build that image, and then we can use it to build containers. And then we'll actually push it to Docker Hub and then use it in our deployment that way. So when we're talking about our laboratory environment, we're going to start with this Dockerfile, and then we're going to build a Docker image from the Dockerfile, and then we'll test it. We'll run containers off of our custom image, and then we're going to push that custom image to Docker Hub. And then from there, we'll use it to pull into our deployment, to our production IIS and Nginx. Or, excuse me, just the IIS website. So that concludes the high-level overview. And now we'll jump in and take a look at the code and then execute that code and begin the configuration of the lab environment. So the lab begins with this build and push image from Dockerfile. So to build the Dockerfile, we'll need to configure a virtual machine. And so we're going to stand up a virtual machine, and we're going to actually install Hyper-V on it. So we're going to do the process to configure the server for nested virtualization. We won't create nested virtual machines, but we will need the Hyper-V role installed to create Hyper-V isolated containers. So in order to install the Hyper-V role on a virtual machine inside Hyper-V, we have to expose the virtualization extensions on the virtual machine. So this first bit of code will build the virtual machine, stop it, expose the virtualization extensions, and then start it. On my GitHub repository, I have a set of functions. One of them is called new-lab_VM. It allows me to quickly create virtual machines from ISO files and golden images. So I'll use it here in the code to prompt instruction to create the virtual machine. You can create it however you want, but this function is super fun and easy to use. So this is how I'll refer to how I'm building the virtual machines as we go through the video. So that's all that we've done here is we've created a virtual machine. We've given it 2 gigabytes of memory, exposed the virtualization extensions, and then we're installing Hyper-V. So at that point, we'll install Docker, and then we'll do some testing with some lightweight images, the main one being this Hello World nano server, just to take a look at a container running in Docker. We'll install PowerShell version 7 on it, check out which user, are we the container user or the container administrator, and then we'll start some containers and process isolation and Hyper-V isolation. Pull in different images, like for example, Windows Server Core 2025, IIS, and then just the standard one. And then just create different containers. For example, this one will run a container in detached mode, whereas if you use IT, you go right into the command line, where detached mode just starts the container, and then we can use Docker exec to run commands inside of the container, like ipconfig or start a PowerShell session. And then when we get these containers images stood up, we'll check out what roles are installed, and we'll see that the IIS Windows Server 2025 image will already have the web server role installed on it, where the Windows Server Core image will not have it installed, but it will have every feature that the Windows Server operating system supports. So at that point, we'll be ready to build our Dockerfile. So we'll just create a folder to put all of the files in, and then we'll use Notepad to open up a file called dockerfile.dockerfile. So your Dockerfile, the extension is actually not important. The text mentions you don't even have to have a file extension. I like to put the Dockerfile extension on there so we get the syntax highlighting in our integrated development environments. For example, I'm using VS Code. This just makes it a bit easier to read. So we're just going to open up the text editor on our Windows server and then copy this into the contents of the Dockerfile on the server. And so for our base image, we'll be using IIS Windows Server Core 2025. And then here we download the JPEGs for the website. And then in this particular image, I use a startup PowerShell script to set variables at runtime so that depending on what your hardware is, the website will display information related to your hardware. So let me get this file open here. So this is kind of where a lot of the magic happens for this particular script. So I define these environmental variables, nothing too fancy to start out with: the computer name, OS version, the date, the CPU. But the important one is the pod IP, because that will allow us to tell us which pod and which node the pod is on. So we'll use the pod IP to figure that out. But then I'll also pull in the number of logical processors and display that on the website. So for example, my host has 10. So on the website, it will display 10 logical processors. If yours only has 5, then it would display 5. So the idea is that these aren't just static variables hard-coded into an HTML page. They are actually dynamic, and they are set at startup. And then we'll see as the containers start up, these values will change. And so when we build the Dockerfile, we use the copy instruction to copy the startup file onto the container. And then we use the run instruction to configure a few more settings. And then we define an entry point, and we do define the startup script right here. So we will copy the contents of this file and then paste it into the Dockerfile on our server that has Docker installed. And then we'll do the same thing with the PowerShell file. We just need to make sure they're in the same folder. And then we'll just copy this text into the server and then save it. And then I explicitly change into the directory before executing the command. And then we use the docker build command to actually build the image. So the name of the file is dockerfile.dockerfile, and then this is the name that I specify of the image. And then this is needed for the command to execute properly. It's a file path. So after a few moments, we'll do Docker images, and then we'll see that our image is available to start running containers. So then we use Docker run --rm to do some testing just to make sure that it starts up, and then we'll run a container in detached mode and then test ipconfig and PowerShell interactive terminals. And the main thing we'll just want to take a look at is just to show that like Hyper-V is not installed, containers is not installed, but the web server role is installed because that's the specific image that we went after. So after we finish up our testing, we will push the image to the Docker Hub. So these are the commands to connect to the Docker Hub. Before we do that, we have to tag the image with a name. So we will give it this custom tag, and then we will push the image to Docker Hub. And then once the image is there available on Docker Hub, we can start pulling it in our deployments. But then we'll actually remove all of the images from our image or the server that we just used to build the Docker or the container image. And then we'll do a test pull so that the only image is our custom image, and then we'll build some containers just to make sure that everything looks great before we move on to the deployment of the Kubernetes clusters. So that's just all setting up, building a custom image that we'll be using in our deployment. You could just skip this part and use just a regular image that you wanted to, but this part of the curriculum is working with Docker files. So I wanted to do a demonstration of creating the image with the Docker file. So now we'll move into talking about configuring the Kubernetes cluster with Windows worker nodes. So the control plane node has to be Linux, and we're going to be using Ubuntu. In order to do that, you have to disable secure boot. So we'll create this virtual machine, disable secure boot, and then install the Linux operating system. And then we'll have 4 Linux worker nodes, each with 1 gigabyte of memory, with just the containers role installed. And this will prove that you do not need a second hyper. We do not need nested hypervising for containers. We just need the containers role. So this is just creating those virtual machines. Then we'll SSH into the control plane. That's how we'll do the configuration, is SSH from in our lab environment. I'll be doing it from my Windows server that is acting as a router and a DHCP server. In your environment, you could do that as well. I've got the link in the description to the video on how to create a Windows server to be a router and a DHCP server, but you also could just use a external Hyper-V switch and let your home router do all of the DHCP and the routing. But you will need some kind of device with a web browser to do testing. That's in the testing lab environment. So the first thing we'll do is install micro K8s. Once we get micro K8s installed, there's some packages specific to micro K8s we'll need. The big one is this host path storage. We'll want to check DNS, but that will already be installed. We'll start to just see some of the pods come online just by getting micro K8s up and going. And then we're going to use a web app called Headlamp, which is a web app. So we'll access it in the web browser to see how the cluster is doing. So we'll monitor it with command line, but then we'll also set up this Headlamp graphical user interface to take a look at how the cluster is operating. So then we'll begin installing Calico on the micro K8s cluster. So we need to figure out which Calico version we have, and then we need to get this kube config file to our home directory. And then we need to pull down some files, and then we need to check that Calico CTL is working. So we'll see that we get the version and the nodes, make sure that IPAM is working, and we need to set the strict affinity to true. So at that point, we can move on to configuring the Windows Server nodes. So the big thing we have to do here is install the container D runtime. We won't be using Docker in the Kubernetes cluster. We'll be using container D. So then I will share that configuration file from my control plane node and then download it to each server. That's what this bit of code is. I make this file directory and then use the invoke web request command to download the config file, the kube config file, to each server. There's also a cert that we need that we'll get off of the control plane node. In practice, it would work like 9 times out of 10, but then I would get this weird error about an X09 certification. And so if we get this cert imported into each Windows server, we won't get that error message. So each server will need this certification. And then we'll just check that it's been installed. And then we'll begin to install Calico. So in this case, we'll be using this PowerShell file. When I ran the PowerShell file, I had to create some folders and define some variables, and then it ran just fine. So you might run it and you might get some errors, but then it's pretty explicit about what you need to do. It could be your environment, might be different than mine, but this particular script, I had to modify it just a bit to make it work. But if you use this link and then define these variables and folders, you should be fine. So when that runs, it makes these 2 PowerShell scripts. We run these 2 PowerShell scripts, just triple check everything looks okay. Make a firewall rule, and then there is the install kube services PowerShell script we have to run. And then one little tricky part, there is this kubeless services PS1, and we just want to get the IP address of the server, and then we have to type it into this PS1 file. And then at that point, we'll check the services, restart them, and then we'll go to the master control plane node, and we'll start to see the Windows Server worker nodes come online. One thing that you can do to speed everything up is pre-pull all of your images. I found it just a bit frustrating. You will do the configuration just fine, but if you didn't pre-pull these images, the deployment will lag because it is downloading these images. So we're going to go to each Windows Server worker node, and we're going to download the IIS Windows Server Core 2025 image and then our custom image from the Docker Hub on each Windows Server node. And then at that point, after all that configuration, we're ready to start talking about deployments. So we'll begin by creating a simple deployment. So we'll do sudo nano, which is just a text editor on Linux. And then we're going to paste this configuration into the text editor. And this is referred to as a YAML file. And then we will use the micro K8s kubectl apply command to apply this YAML file. And the big things here, our replicas are 6. That means we're going to make 6 pods. And then we'll begin scaling. We'll begin experimenting with the number of pods that we can run. But in the first test, we'll just do 6. And then we can see we've defined our image, which is going to be this Moose Lover custom IIS image. And then another important part is we are, in the first example, we'll be doing node port. So we'll take the IP address of the control plane node and then put a colon and 380 to access our container websites. Then we'll do some testing with the deployment, and then we'll actually tear down the deployment, and then we'll use a technology called Metal B that will allow us to use a separate IP address from the control plane node to access the website. So essentially, we'll be using 192.168.11.100, and then every time we put that in a web browser, it takes us to one of our containers. So we'll see we'll have all these different IP addresses, or different pod IP addresses, all connected to the same address. So the idea is you type in the same IP address, it takes you to what looks like the same website, but they're actually running on different containers. So then we'll start a brand new deployment YAML manifest. This time we're going to use 12 containers. We'll use the same image, but we're just going to be using the standard ports because we'll be using Metal B. So we won't be using any funky ports. And then we'll apply that configuration, watch everything come online, and then we'll start pushing it to the max. During testing, 50 pods completely crashed my system, 21 was fine. So for the video, we'll at least create up to the 21 pods just to show the efficiency. So the lab environment will have 5 virtual machines, which actually 6 when you count my router. My memory is completely maxed out. I couldn't stand up another instance of IIS if I wanted to. But then all of a sudden, we will have 21 instances of IIS running the website. So that concludes the Kubernetes cluster with Windows worker nodes. And so now we'll talk about the Linux worker nodes. So during testing, I found the more memory that I used, the better everything performed. The control plane node says it only needs 1700 megabytes of memory, and sometimes 2 gigabytes would work, but sometimes it wouldn't. And I found giving it 3 gigabytes keeps it pretty happy. So for my particular host, I've only got the 16 gigabytes of memory, so I am kind of limited. So we'll only be doing 2 Linux hosts running at 2 gigabytes of memory. But again, they seem to just perform better with the 2 gigabytes of memory. So when installing this Ubuntu image on Hyper-V, we must disable Secure Boot. So you can see we're disabling Secure Boot on each device. And then we prompt through it and install the Linux operating system on our 3 virtual machines. So then we'll configure the master control plane node first, and we'll use the sudo nano, which again is just the text editor, and we'll create this initial config.sh shell file, which is this file right here. And so the shell file is just executing a series of bash commands. So instead of just doing them one at a time, I can do a whole bunch of commands in one little file, execute the file, and all of the commands will execute. So the big things that we're doing here is installing our container RD packages, and we're getting kubeadm, kubelet, and kubectl. Some of this other stuff just has to do with how you get into the Kubernetes repos and some other things that we have to do, like disable all possible swap entries in fstab. And so what happens is, as you go to stand up your cluster, you'll get these errors, and then find that on every server on the Kubernetes cluster, control plane or not, will need the elements that are in this initial config shell script. So then we apply it by just doing sudo bash the name of the file, and then we'll check the version of kubeadm, kubectl, and the kubelet. And this is another one of those things we'll want to pre-pull our images so that we control the time. We don't want to be doing our deployment and then all of a sudden there's a hang. So we want to be proactive and pre-pull everything that we can before we start initializing deployments so that we don't get hangs. So we'll do the sudo kubeadm config images pull. So after we get those config images, then we can start initializing the control plane, which is a big milestone in getting your Kubernetes cluster set up. And then we do need to move this kubectl to our home directory. Then we're going to grab some YAML files off the internet and use kubectl create to apply them. And what we're doing here is we're using something called the Tigra operator. And this deploys, this YAML will deploy the operator that manages Calico, and it's the modern recommended way to install Calico. So we'll see these Calico pods come up, and then we'll initiate the deployment, and then install Calico itself, and then make sure that we have the node in a ready state before we move on. So we'll see the only node in our cluster will be the control plane node. We'll see that it has that role, but we need to wait until it goes from not ready to ready before we proceed. So in our configuration, we did a lot of pre-setup that it will most likely go in pretty quick. But if you miss some of this stuff, like pulling the images and stuff, it might take longer for your node to come online. So just give it 5, 10, even 15 minutes. But if you do everything perfect, it should come on quicker than that. So at this point, we're ready to begin joining nodes to the cluster. So the Linux worker nodes have the exact same initial config shell script that needs to be run on them. So we'll just repeat that same step. And then we'll pull in some of these other images that are needed so that we don't get those hangs. At that point, we print the token off of the control plane node, and then we start adding the node to the cluster. And then we'll officially have our Kubernetes cluster set up. And then at that point, we'll do something with it. And that's when we're going to set up the custom website using Nginx pods. And then we're going to leverage Metal B again. So we need to make sure we have these Metal B pods come online. And then the Metal B in this instance, since we're not using micro K8s, we're doing a Kubernetes control plane node from scratch. We will have to have a Metal B config YAML file. And this defines like the IP address range. So for example, in the previous Windows worker nodes, we'll be accessing it with 192.168.11.100. And these examples we'll be using 200 because we set it here in this YAML. Then we need to set up an ingress Nginx deployment. So again, we will leverage a YAML file that is out there on the internet at the GitHub user content. And then we need to make sure that we have that ingress pod. And then there is a patch that is recommended that we'll do, and this is so Metal B will assign an IP address. And then we'll just need to make sure that we have the service. And then we'll want to pre-pull this Nginx Alpine image, but it's so small that it's not that big of a deal. And then we're finally ready to make the deployment YAML file. And so the magic in the previous one happened with a startup PowerShell script and the Dockerfile. So the magic in this one actually happens in the manifest. So here I am defining variables like the name of the computer, the pod IP, the CPU, information about the operating system, information about the processor, and then I'm downloading a custom website from my GitHub and then replacing the text in the HTML file with my custom variables that are defined at runtime. So we get the exact same behavior so that the elements on the website are dynamic. It depends on the hardware that you're running, what values are displayed on the website. And so then the key right here is using this sed command, and then this will kind of replace some of the text with the characters that we want. So like, for example, we'll have logical processor count, and then we'll get the number of logical processors. We'll be using 9 replicas, and then just like in the previous example, we'll start scaling it up. And it does, you can see other factors. I won't go into each line because it's kind of a whole nother curriculum set. But you can see like the image right here is Alpine 3.9. Here I'm getting the custom image from my GitHub repository. There's stuff that we could talk about, mount points, and then the container ports, information about the volume, and the ingress class name is Nginx. And then so once we copy and paste that in there, we will apply the YAML file, and then watch our pods come on, and then scale the deployment, and then just begin testing. Okay, excellent. So we talked about each Kubernetes cluster, and then I'll just give a brief overview of the nested Hyper-V virtualization script. So all we're going to do is just create a new virtual machine, give it as much memory as we can. I might give it 6. I might try 8 during the video, but 4 for demonstration is fine. And then the main thing is we have to expose the virtualization extensions so that we can install the Hyper-V role. And then we, inside of our nested Hyper-V host, we'll have to create a Hyper-V switch. And then we'll also have to enable MAC address spoofing so that the networking works properly with the nested virtual machines. And then we'll just stand up a few nested virtual machines at the end of the lab. So that will conclude the high-level overview of the entire lab, and then an overview of the code. So we're now ready to begin executing the code and configuring the lab environment. So I'm going to go ahead and connect into my Hyper-V host. So here we are on the Hyper-V host, and before we start the lab, we will take a look at the specs of the computer. So I'm using a Dell XPS 9520. It's running Windows 11. It's got 16 gigabytes of RAM, 2 8 gigabit sticks, Intel Core i7 with 20 logical processors. I'm using a Windows server as a router and a DHCP server. So I have some Hyper-V switches on my host. So I have several private switches and then one external switch that allows access to the internet through my Wi-Fi adapter. So here in Hyper-V Manager, we can see my Windows server that is acting as a router and a DHCP server. And then I've also stood up the Windows worker nodes that we'll use in the first Kubernetes cluster. And I have renamed their computer names and installed the containers role. So before we begin configuring the Kubernetes cluster, we're going to build our custom container image from a Dockerfile. We'll be creating a virtual machine called micro K8s node Docker build, and we'll use this virtual machine to build our container image. On my GitHub repository, I have a set of functions that allows me to create virtual machines quickly. The link is in the description. And so I'll use these functions to create this first virtual machine. And we'll give it 2 gigabytes of memory. And we're going to use the generalized image of Windows Server 2025 desktop experience. So we can see the virtual machine has been created. And we're going to go ahead and set the default password. And then we will expose the virtualization extensions. So we're using a golden Hyper-V image. So my golden image has 2 accounts programmed into them alongside the administrator account. So there's administrator, Mega Man, and Rush. And they're also set with a default background image. So when we see the virtual machine start up for the first time, you'll see that it doesn't look like a normal instance of the default Windows Server. But that's because we're using a golden Hyper-V image. And there we can see Mega Man and Rush in the administrator account. So we'll need to expose the virtualization extension so we can install Hyper-V. So we need to stop the virtual machine, expose the extensions, and then start the machine. And we can see now that the virtualization extensions have been exposed. So if we don't expose the virtualization extensions and we go to install Hyper-V, we'll get the error. So we won't have that problem because ours are exposed. So we're going to rename the computer and then install the Hyper-V in the containers role. So this will take just a moment. So I'm going to pause the recording to compress the video just a bit. Okay, excellent. So it just finished installing the role there. So our first task will be to install Docker. Go ahead and get connected here. So we'll be installing the Docker via the command line using install module. We'll need the Docker MSFT provider, and then we'll use invoke web request to get this PowerShell file. So now we just executed the PowerShell install script, and we can see now we've got Docker installed. So we're going to go ahead and do a quick test for Docker. So we'll see what images we have just to begin with. You can see we've got no images. So now we're going to pull in the Hello World Nano Server image. So this is a smaller image, so it should pull in relatively quick here. Okay, excellent. And so now we can see we've got our first image on our server running Docker. So now we're going to create our first our first container. And now we're in CMD. So since this is a very lightweight image, it doesn't have PowerShell installed. So as a test, that will be our first goal, is to install PowerShell version 7 on this container. So I'm just downloading the zip file from the internet, extracting it, and then running the PowerShell version 7 from the extracted folder location. Okay, and a good reason to do that is we can quickly figure out what our username is, and it is container user. We also got some other information about the processes and services, and then what version of PowerShell, which is PowerShell version 7. And interesting to note, it shows the OS as Windows NT. So we could see that we ran the container as a standard user. So now we'll try to run a container as an administrator. So we install PowerShell version 7. We can see we're the container user on that container. So now we'll create a new container, but we'll run it as a container administrator. So now we'll do the same thing. We'll install PowerShell version 7, and then we'll see what our username is. And now we can see we're logged in as the container administrator. And then we can see the two pods here and their statuses. So we're going to go ahead and remove them. remove the containers. So now we're going to create containers and the different isolation modes. So we actually just created containers running in process isolation. Those were the first two examples. It just defaulted to them. So for the video, we'll skip that first one, and we'll just create a Hyper-V isolated container as the administrator. And so the reason that this is possible is because we exposed our virtualization extensions, installed Hyper-V, and now we have the capability to run a container in Hyper-V isolation mode. And then just going back to the diagram. So we created our first containers that were just standard process isolated containers. And now we have created the Hyper-V container on our virtual machine here. Oh, and that, I forgot, I did not have the temp directory created there. So we'll just install PowerShell 7 there. When I ran this set, I did not have the directory created. So let's take just a moment. And so now we are the container administrator on the Hyper-V isolated container. So we're going to remove all of the containers. And so now we'll pull in a couple of images to test with. So we're going to pull in the IIS Windows Server Core 2025 image and the Server Core 2025 image and just kind of compare them. So we'll use the Docker pull command to pull them from the official Microsoft container registry, the MCR. So these images will take a moment to download, so I'm just going to pause the recording to time compress the video. Okay, excellent. So the images are now pulled, and the second image pulls almost instantly because it parts of the image already exist on the server. So when you go to pull the other image, it's much quicker. So excellent. So now we've got our images. So we'll do a test here. So we'll create an Hyper-V isolated container as the administrator. We'll call it beat DC01, and we'll use the full server core container image. And one of the things we're going to look at is the features that are installed. If we do git Windows feature, we'll see a list of the available roles and features on the OS container image. And you can see, since it's server core, we've got all of our different roles. We can even see the Active Directory roles, DHCP, DNS. But the web server, containers, Hyper-V roles, those are not installed on the image. So one more test, we'll run this one in detached mode, but we'll use the IIS image instead of the server core image. We use the exec command to enter the interactive terminal session for the container. And when we look at the features that are installed, we'll see that the web server IIS role is installed. So if we use the server core image, our custom image wouldn't work because we need this role installed on our containers. So I'm going to remove all of the containers. And we're now ready to build our custom image from our Dockerfile. So I'm going to create this folder, and then we're going to create a file called dockerfile.dockerfile. And then we'll paste the contents of our Docker file into the server. And then for this particular configuration, we also need a PowerShell file in the same location. So we'll use Notepad again. And we'll copy the contents of our startup PowerShell file. So at this point, we're ready to build our Docker file. So I'm going to change to the Dockerfile directory where we have our Docker file and our PowerShell file. And so now I'm going to use the docker build command and build the image. And this is really neat. It gives us information about the error. So step one, it's using this IIS Windows Server Core as the base image. It's coming in here, pulling down the different files needed for the container. And so now we have finished our build. And when we look at images, we now have our custom IIS with micro K8s image. So this is used for testing. We'll go ahead and just run one in detached mode to get the IP address. So we're going to build a container from our new custom image built from the Docker file using the docker run command, and then we'll just reference our new custom image. And then we'll get the IP address of the container by using docker exec, the name of the container, and then the command will be ipconfig. And so now when we plug this into the web browser, we can take a look at what the website will look like when we stand up the Kubernetes cluster. So this computer name was pulled at runtime from the startup file. So if we go into the container and we get the computer name, we can see it's this 733 ends in 632. And so that computer name was pulled at runtime and then embedded into the website. It also pulled the operating system, the time of date, and the number of logical processors. So when we look at our virtual machine, in this particular example, I give the virtual machines half of the amount of logical processors of the host. My host has 20, so all my virtual machines get 10 virtual processors. And so that's why the number pulled in, or the website pulled in the number 10. So this is neat. When you run it on different infrastructures, you'll get different results depending on your hardware. And then it also pulled the installed role and found the web server IIS role. So a lot of this information was dynamically assigned during the creation of the container. And then we also just get the standard website information, like all of our pictures and text formatting. So we're now ready to push our container to the Docker, or to Docker Hub. So we'll go and check out my Docker Hub, that account where we will push the images to. So it's really easy just to go to hub.docker.com, create a free account. They have a little demo. You create this public test. And then a couple weeks ago, I created the exact same project, but using Windows Server 2022. And so today we just did the exact same process, but with Windows Server 2025. And now we're going to push it to the Docker Hub so that we can pull the image down during our deployments. So it's pretty straightforward. It's just Docker login to connect. And now we are connected to the Docker Hub. So again, these are our images, and we're going to be pushing this image. But before we do that, we'll want to give the image a tag. So we're going to come in and tag the image. And now under repo tags, we'll see the name of the custom tag that we just programmed in. So repo tags, now we have this custom name. So we're now ready to push our image to the Docker Hub. So we built our custom image using a Dockerfile, and now we're going to push the custom image to our Docker Hub repository. And this part does take just a moment, so I'm going to pause the recording just to time compress the video just a bit here. Okay, excellent. So now we have officially pushed the Docker image to our Docker Hub repository. So we'll test out Docker search. So it searches the Docker repository and then it finds our custom image. So now we're going to do a full-on test. So right now we have all of these images, but I'm going to remove all of them. So take just a moment. So we'll give it just a moment to delete all of the images that we've been working with. And then after the images are deleted, we'll pull in our image that we've pushed to the Docker Hub repository. So I'll bring back the website here. I'll hit refresh. And now we can see that the custom IIS site with micro K8s Windows Server 2025 image is now available here on the Docker Hub. And then we also saw it with the Docker search. Okay, it just took a second for those images to be deleted. And you can see we have no images. So we're going to go ahead and pull our custom image from the Docker Hub using the docker pull command. And then this will take just a moment, so I'm going to pause the recording just to time compress the video. Okay, excellent. So now we'll check our images. And we can see the only image that we have is our custom image. So we'll go ahead and run a detached pod. And then we will get its IP address using Docker exec. So we'll plug in the IP address. Now we have our website. You can see the computer name is 9B8, ends in A0. And the container name 9B8 ends in A0. So you can see it pulled in the computer name and all the other stuff at configuration time. So that's pretty neat. We were able to take a txt file, a Docker file, build our custom image, push it to our Docker Hub repository, pull it down, and then create containers from it. So that completes our first task for just getting the custom image. Now we're ready to move on to stand up our Kubernetes cluster with Windows worker nodes that will pull down this custom image to then run the website. So the first step is creating the master control plane node for the Kubernetes cluster. So currently, as I mentioned before, I have the 4 worker nodes already created in Hyper-V. They've had their computer name set, administrator password set, and then they have the containers role installed on them. But we need our Linux control plane node to orchestrate Kubernetes between the nodes. So that's the task we're on right now. So here I've got my custom functions to create virtual machines. This time I'm going to use an ISO file. So I'll be using the Ubuntu ISO file to install a operating system. In this case, it'll be Ubuntu. So in order to do that, we must disable secure boot. So we're going to go ahead and create this virtual machine and then disable secure boot. So we can see the virtual machine is running. And since we've disabled secure boot, we now can access the installation wizard. So as I mentioned before, my Hyper-V router is also a DHCP server. So the Linux box will get its IP address from the DHCP server. If you're using the external Hyper-V switch, it will get it from your home router. But there you can see the IP address from my DHCP server, the 192.168.11.0/24 network. And the address right now is .61. It will increment 1 after the installation wizard, most likely. So it'll probably be 62. So now it will test network connectivity, look at the mirrors. And then once it's happy with the mirrors, we can move on to the next screen. So we're going to use the entire disk. So you program in your name. The server's name will be micro K8s. We're going to do admin 01. And program in a password. We will not do Ubuntu Pro, but we do need OpenSSH. So we will SSH from our RAS server to do the configuration. So now the Linux operating system will finish installing, and I will pause the recording here just to time compress the video just a bit. Okay, excellent. So the installation has finished. So we'll reboot. One thing I've noticed when you do Ubuntu on Hyper-V, when you finish installing the operating system, you get this prompt about removing the installation media. Make sure you hang around long enough to press the Enter key and get back to the login screen. And then we're actually going to log in. Then we will get the IP address, IPADDR. I like to use grepETH. So .62 is the IP address of the control plane node. So I'll make note of that here. So we're now ready to SSH into our control plane node. So we can't copy and paste from the Hyper-V terminal, but I found that if you use SSH from Windows Server, then we can copy and paste. So here I am on my Windows Server 2025 server that's acting as a router and a DHCP server. And we'll be using the command line to use SSH to connect to the Linux control plane node. Let me just resize the window. Now we're logged into the same machine, just via SSH. So we're going to install micro K8s. We had the option during the installation wizard, but we're going to use the snap install command to install it. Excellent. So now we will start it and check the status and the version. And then we can see that it's running, and then we get the version. So we have to add ourselves to the micro K8s group. So we'll use sudo usermod to achieve this. One thing to note, we won't be added to the group unless we exit our SSH session and come back in. And that will refresh. We'll now be a part of the micro K8s group. So the DNS is installed by default, but for this particular lab instance, we will be using host path storage, and this creates a simple storage system using our machine's local disk. So we will need this enabled. Excellent, and now it's installed. So we'll check out some of the pods. And we can see we've got some pods running. So that's pretty neat. We've already got pods up and going. So before proceeding, we're going to set up this headlamp, and this is a graphical user interface so that we can look at the cluster through a GUI. So I tell micro K8s about the repo, then we're going to update the repo, and then we can install headlamp. We get this great message about happy helming. So now it's deployed, and we'll need an authentication token to access it in the web browser. So that's what that string of characters is. And then we'll have to actively have port forwarding. So when we want to use it, we'll have to start in a shell the forwarding process. And then we'll be able to access the graphical user interface through the web browser. And we specified port 8080 right here when we open the port up. So we plug in the IP address, port number. So now we'll plug in the IP address plus the port. And then we need the authentication token. And so we will use the command line to look at all the same information, but this is a neat little graphical user interface. And you can see we've already got 5 pods and a node. And so then we can check out different information about the nodes or the pods. We'll kind of come back after we set up the cluster and look at the different pieces of the cluster. So the next part, we're going to start getting Calico set up, and we need to know the exact version. So we'll go ahead and run a few of these commands. And we can see the Calico version here is v3.29.3. So we'll define that variable and use it when we use the curl command. And then we also need to move the kube config file to our home directory. So we'll go ahead and do that. And now we have this in our home directory, and then we're going to share it to all of our servers, and then we need this string of text, this output needs to go on each Windows worker node. So we'll go ahead and just check the status. And we can see micro K8s is ready, but it doesn't have any roles yet. So we'll continue on and do the Calico part. So we're going to grab Calico, make that variable, and then we'll run the Calico version command to see what version of Calico we've got. And then we'll also look at the Calico nodes. So here's our Calico version information, v3.29.3, and then the Calico node micro K8s. So we do have to set strict affinity to true. And then if you're wondering what the status is, you can use this show command. And this will tell us that the strict affinity is set to true. So we're now ready to begin configuring the Windows configuration. So I'll go through it one time, and then it's rinse and repeat 3 times. So I'll start up micro K8s node 1, and then do the nodes one at a time. And you can see they have the containers role installed. So the first thing we need to do is install containerd. So we'll grab the PowerShell file and install the runtime. So now we're going to share out the kube config file so that we can download it to our server. So we're going to create this K directory, and then we have to plug in our IP address for the control plane node, which is 192.168.11.62. And then we'll download the file using invoke web request. And now we can see the config file is on the Windows server. So now we have to do the same thing with the certificate. And we should be able to start another SSH session. And so now we've moved this cert that we need to my home directory, and then now we're going to share it so that the servers can use the invoke web request command to download it. So we're using HTTP server from Python. And actually we can only share one at a time. So I'm going to stop him, and then we can start sharing the other one. And now the same thing, we need to plug in the IP address of our control plane node to get that certificate. And we'll do this all in one shot. We'll create the directory, get the certificate, and then import the certificate, and then make sure that it all succeeded. And now we can see we've got our certificate imported. So we got a certificate from our Linux control plane node, and now it's imported to our Windows server. So now we're going to retrieve and install Calico. So we grab this PowerShell file and install it. So we'll go ahead. Now that we have the PowerShell file, we have to create a few directories and environment variables, and then we'll execute the PowerShell command after we specified some information about the DNS server IPs. For example, the service CIDR, classless interdomain routing, release space URL. So we'll go ahead and run the PowerShell script. And this will take just a moment to run here. And so it will create a couple other PowerShell files that then will run, but we will let it finish. And then this part does appear like maybe it's erroring out, but this will just kind of increment like this for a second, and then it will stop. Excellent. So now there's these two other PowerShell scripts that were created that we need to run. So that one starts Calico. The other one installs it. And then we'll just want to triple check the configuration is going well by looking in the program folders file. Everything is looking great. So we will need a firewall rule, and then we do need to install the Kubernetes services kubelet and kubeproxy. This next part is a bit tricky. We have to alter a PowerShell file. So the IP address of the Windows worker node is 192.168.11.63. So we have to plug that right here. And then I like to explicitly close this out. We will save it. Now we'll restart everything. And now we can check on our control plane node the status of our nodes. So we can see we've got our micro K8s. It's in a ready state. And now we have joined Windows Server 2025 Data Center to the cluster. So now we just need to rinse and repeat on each node. So rather than repeating myself, I will record me doing the configuration and then dub in the music that I'll be listening to. I'm just going to jam out and rinse and repeat the same process that we just did on the other three nodes.
Looking down on the cars on the highway, a stream of taillights, everybody advancing together, do so willingly sacrifice rights. When people accept their cogs in the system, give up free will, conform, individual pieces of this world together and become a force storm. Looking down on the burgeoning sea, the skyscrapers rise, even men with the greatest intentions stop believing their own lies. We can borrow from the future, but eventually someone's got to pay. The only way out of the cycle is to strike out and pave your own way. Will you fuel the desire when always struggling with the truth of the life that might have been? But no matter how jagged your path is, you'll always come back to the road when the dust of the battle settles. The war still rages within.
Excellent. So we're going to have our third node added here in just a moment. So we just need to finish out the config here. So 65. Then we need to start everything, start the services. And excellent. When we come back to our control plane node, so we've now got 3 worker nodes. So we've got our Kubernetes cluster with a Linux control plane node and 3 worker nodes. So I just killed the music, and then we will do this one more time just to review everything. So here we need to share out the kube config. And then we will begin adding the last node to the cluster. And it's the same process that we just did. We're just rinse and repeating. Containers role is installed. So we'll install containerd. Excellent. So now we're sharing the kube config already, so we're going to grab it. And we can see we've got the kube config file. Now we'll share out the cert. Then we're going to grab that cert and install it on our Windows server. Excellent, and now we're going to grab the PowerShell file to install Calico and run it. This part will take just a moment. Excellent. And then after we get through this last prompt, we'll just have a few more commands, and then we'll have our fourth node added to the Kubernetes cluster. Okay, excellent. So it's wrapping up the configuration here. So we'll run these two PowerShell scripts to install Calico and start it. And then we'll get the kube service installed, add that firewall rule, and add the IP address. It was 59. Excellent. So now we've reached a big milestone in the configuration. We reached the milestone when we joined our first node, but now we have our master control plane node, which is Ubuntu, running 4 Windows Worker nodes. So now that we have this amazing Kubernetes cluster, let's do something with it. And we are going to stand up a IIS website with our custom image. So to keep control over our deployment, we'll want to pre-pull our image on the servers, and we'll also get the IIS Windows Server core image as well. So we'll pop into each worker node and then download these images before proceeding with the deployment. This does take a bit of time, so I'm just going to pop into each server and start the download. And then on the last node here, we'll pull the same images. All right, excellent. This will take just a bit of time, so I'm going to pause the recording to time compress the video just a bit. Excellent. And now we just finished our last pull here. And we'll just check the other nodes. Looks good. Node 2 looks good, and node 1 looks good. So we'll get back here to the control plane node. So we're now ready to create our first deployment. So we'll use sudo nano, which is just a text editor in Linux, to open a file called iss-simple.yaml. Some of the main things to look at in our configuration is we'll start with 6 pods using our custom image, and it's going to use port 380. So we're going to paste our YAML config into Nano, save it. Now we'll apply it. Excellent, and now it's been created. And now we'll watch the pods come online. Now we did a bunch of work ahead of time so that our containers won't lag very much when they get created, but depending on the steps that you took, if you missed a step, this might take a second for your containers to get created. But we'll see them start to come online here. So we use watch. And while we're waiting, we can actually use the describe command to figure out what the status it is in. So we'll just grab a container name. We'll define it here in this variable pod. And so we can see the pod has initialized and it's still coming online. So we'll get messages down here as it starts to come online, but we can see it was assigned to node 3. Excellent. So we've got some statuses changing from container creating to running, and they're getting IP addresses and stuff. And so we want this ready status to change from 0/1 to 1/1. We can see the container is now going through some different steps. We can see it's found the image. It was already present on the node that it was scheduled to run, K8s node 3. If it wasn't, it would start pulling and there would be a lag. So since we did the work ahead of time, the container should start a little bit quicker. So now we can see we've got some of our first pods coming online here. So we've got 3. So we'll just kind of wait for the other 3 pods to come online before proceeding. Okay, now all of our containers are up and running. And so the IP address, I believe, is 62. So .62. And then we have to use port 380 to access the website. So we'll come into our web browser. And then we get access to one of the containers. One thing to note here is we're using the IP address of the control plane node. So we will alter the deployment and use a separate IP address in the next example. But real quick, we'll just start opening up new web browsing windows, and we will see the IP address start to change. And so what that means is we're landing on different containers, even though we're navigating to the same web address within the same port. So for example, this information was all pulled at runtime, so the logical CPUs, the IIS role, the processor, the date, OS version, and computer name. In this particular deployment, I've made the computer name all the same. So that was just how I set this deployment up. So now we're looking at this IP address, and if we bounce back to the control plane node, and we'll look for 10.1.220.67. So that is on node 3. I shouldn't have closed those. So we'll just do a couple more. So 10.1.91.133 is on node 2. So even though we hit the same web address and it looks like the same web page, we've technically landed on a different server or a different node. And then we can see we get all of our images, and the rest of the website is the same, identical between the sites, except for the information here at the top, where some of the information is pulled at runtime. So now we're going to scale the deployment up to 9 replicas. And so now it's scheduled 3 more containers, and then we'll start to see them come online. So go ahead and use watch. And so this is an illustration of orchestration. The master control plane node is figuring out which nodes to place the containers on, starting the containers, getting the container IP addresses, and allowing us to scale the deployment from its original. Okay, we got 1 container that just came online, so we'll just wait for these other 2. And now we have 9 containers online. So we started our deployment, and now we've scaled it up. So now we're going to tear down this deployment and set up a new deployment. So now if we look at the pods, they'll go into a terminating status, and then they will disappear. Now, if we just deleted the pods, they would actually keep recreating themselves until we completely destroy the deployment. And I did that with the kubectl delete deployment. Grace period equals 0 and force. And so that gets rid of the deployment. So now we're going to leverage metal B, and we're going to use the micro K8s method to install it. And then before proceeding, we'll just want to make sure that we see metal B pods before we try to set up the next deployment. And there we can see metal B is enabled. So we'll just triple check the pods. And this one is still coming online. And now it's online. So now we will create a new deployment. And we're just using Nano, which is just a text editor in Linux. And in this deployment, we will use 12 replicas. We'll use our custom image. But this time for the node port, we will just use 80. And then we will use 192.168.11.100 to then access the custom website. So we're going to grab this YAML config, paste it into Nano, save it, and apply it. So we can see it's applied. We'll just check the service. And we can see the IIS service, and it's a load balancer. And here's the cluster IP, and here is the accessible IP. So now all we have to do is plug this address into the web browser to access the custom site. So now we'll see our 12 containers, or 12 pods, and how they are all coming online. So they all would have said container creating. Now they have switched to running, and then we should see them start coming online. And I might time compress the video just a bit here, although 2 just popped in. But I may, or here's 3, so they're starting to come online here. And now they're all online. So now we've got 12 pods up and running. And now the way to access the website is by using 192.168.11.100. And now, instead of using the control plane node's IP address with a port, we're actually using a completely separate IP address that we can then dedicate to this deployment. So we'll see 10.1.45.136. So we are on node 1. 220.70 node 3. Excellent. So everything is looking very good. Now we'll conclude this piece of the lab by scaling this deployment up to 21 replicas. So we'll come in here. So what's very interesting, so when I began turning these virtual machines on, I had to turn everything on my machine off, even the Hyper-V manager windows, just to get these machines started. So I'm completely maxed out. If I wanted to create another virtual machine to stand up an IIS website, I couldn't. I'm completely maxed out. But here, with containers, since everything is much more efficient, we were able to stand up 21 instances of IIS by using containers. So here are the 21 instances. They're just coming online. So each pod has its own instance of IIS. So it's just unbelievably fascinating, the technology behind this. So this is a big buzzword in the industry right now. And this is a great overview of how to create a Kubernetes cluster with Windows worker nodes. So we'll let these last few come online, and then we'll do one last round of testing. Actually, they might. Let's go ahead and use the watch command. So we're getting pretty close. One. Just waiting for 5 or 6 more. Okay, excellent. We've created 21 pods, 21 instances of IIS. So let's go ahead and just do a round of testing. So 10.145.136 is on node 1. So 91.136 is on node 2. $81,201 node 4. So that was a way that I figured out to match container to node, or pod to node. So for my environment, I tried to scale up to 50 nodes and it completely crashed the environment. The whole system freezes. You have to do a hard shutdown. Then you have to get to Hyper-V fast enough to completely shut down and basically just destroy your cluster. So somewhere between 20 and 50, the deployment will stop working. Before moving on, I forgot we need to take a look at headlamp. So we'll come back up into the configuration here. And so we need to open up a port. So we've got that open. We'll need an auth token. I must have not copied that. All right. Okay, excellent. And now we are on headlamp, and we can see we have 5 nodes and then 28 pods. So we can come over here and look at the nodes, and we can see. Oh, I thought maybe this let me adjust. But here's micro K8s, node 4, 321 micro K8s. And so this just kind of gives you a good dashboard when you're looking at your Kubernetes cluster. And so here are the deployments. We can see our headlamp deployment and then our specific IIS deployment. And that's the one with the 21 pods that we scaled up to. So these other ones are kind of like support pods that micro K8s is utilizing to make everything work. And then here is our actual deployment that we created. And then we can take an even deeper look at the deployments and some of the settings. So replicas 21 gives us a bunch of information. And then network. Kubernetes networking is also fascinating. The curriculum doesn't really dive too much into the networking side, but this is a great place to see. We can see our Metal B deployment and how it looks perfect, and the Cube DNS. So this will conclude the first Kubernetes cluster configuration with Windows worker nodes. Now we'll move on to the Kubernetes cluster with Linux worker nodes. We're now ready to build our second Kubernetes cluster using Linux worker nodes. So we cheated just a teeny bit with the Windows worker nodes by using micro K8s. This time we're going to take a Virgin Ubuntu Linux server and turn it into the control plane node. So as with the other Kubernetes cluster, I'm using a Windows server as a router and a DHCP server. And then I've gone up and stood up the Linux worker nodes with 2 gigabytes of memory. So I've just installed the Linux operating system and that's it. And they are up and running. So now we are going to create the control plane node called K8s. We're going to give it 3 gigabytes of memory. All right, excellent. So we got it started. So I'll just run through the installation wizard here. It's just checking the mirrors. Server's name is K8s, admin 01. And we need SSH. So now I'll pause the recording while the operating system installs, just to time compress the video a bit. Okay, so the installation has just finished. So I'm going to go ahead and reboot. And then there is the IP address. So 71 is the IP address. So now that we have all of the Linux machines stood up, we'll configure them via SSH. And we'll be doing this from the server that is a router. Just resize this real quick. So that was 71. Now we're on K8s. So we need to get on the other nodes. Just try. So I found one. 100% sure which one it is. K nodes 1. Excellent. Well, we'll try 70. So I could have just gone to the terminal to get the IP address, but I was able to figure it out. So now this is pretty neat with Windows Server 2025, Windows 11. We get terminal, and terminal lets you have these super convenient tabs. So now we are SSH'd into each of the Linux boxes. So we're connected to all 3 of the Linux nodes. So each Linux node will need this initial config file. So we'll use sudo nano initial config.sh, and that will use the nano text editor Now we will paste our initial config into the text editor. We'll save it and then run the config with sudo bash. And so this will install containerd, kubeadmin, kubelet, and kubectl. Okay, excellent. We'll just check the version, Kubernetes version 1.30.14. So to make this go more smooth and have control over the deployment so we don't get lags, we're going to pull in some of the config images. We're going to explicitly pull them in ahead of time before we do the deployment. And then once we get those config images, we'll actually initialize the control plane. So let's take just a moment for these to get downloaded. All right, excellent. So let's initialize the network or the control plane. And then we'll want to set up kubectl. And so we can see that the control plane is now set up. So we'll go ahead, set up kubectl. So now we're going to install Calico with the Tigra operator. And this is the modern and recommended way to install Calico. So we'll go ahead and apply this YAML file, which is from Project Calico. And then before proceeding, we just want to make sure that we have the Tigra operator pod. So it's up and running. If this were to not be up and running and you went to proceed, you would run into problems. So we've got our Tigra pod up and going. So now we're going to do the deployment for the Tigra operator. And the condition is met. So now we will install Calico itself using the custom resource YAML. So everything is going excellent. And so now at this point, we'll watch our nodes come online. So this is a little bit different from the micro K8s. Here we see we've got the K8s. It's actually in the not ready state, but it has the role of the control plane. So now after a few moments, we'll see the status change from ready to not ready. Or excuse me, from not ready to ready. So we'll give it just a moment here. Excellent. And in 2 minutes, it changed its status to ready. So if you didn't pre-pull images, if you didn't do the certain configuration that I did, that part might take longer because implicitly other downloads, other configuration files may be downloaded and executed where in ours we pre-pulled the images ahead of time. We use specific packages. And so now our Kubernetes cluster is up and running. It's online with our master control plane node. And now we need to start joining nodes to the machine. So as I mentioned earlier, all 3 machines will get that same initial config file. So we'll go ahead and apply it to the 2 machines. So you can see how valuable the bash files can be when you have a series of commands that you need to execute. Now we can just execute them with one command. Just check the Kubernetes version and looks good. And check Kubernetes version v1 3014. So we need to pre-pull some more images so we don't have any hangs. And we'll want to do this on both nodes. So once those images pull, we'll be ready to add the nodes. And the way this works is we will get a token from the control plane node, and then we'll run this command to join the Linux worker nodes to the control plane, or to the Kubernetes cluster. So that's why it's vital that the machines must have kubeadm to be able to join the cluster. Excellent, so we've got our images pre-pulled. So in this particular case, we have to put sudo first. Depending on your configuration in your lab, it tells us just to run kubeadmin, but we need to put sudo in front of it. And then we get this nice message that the node has joined the cluster. So we'll take a peek. Now we'll just, and now very quickly it changed to the ready state. And most likely that was so quick because of the images we pre-pulled. So now we will join the second node, and it's the exact same command, same token. And now he has joined the Kubernetes cluster. So we'll give him a moment to connect. Excellent. And so we officially have a Kubernetes cluster with Linux worker nodes. So now let's do something with it. So since this is all Linux, we're going to use Nginx instead of the IIS platform on Windows Server. So the first thing we need to do is configure Metal B. So we use micro K8s to install Metal B, but since we're doing a virgin install, we'll use kubectl and get it from the git user content, get it from git. And it's the Metal B native YAML manifest. So we'll apply it. And then we'll just want to make sure that we get some metal B pods before proceeding. So this can trip you up. You start running, and if you just go too fast before these pods are created, you'll run into issues. So you see they create pretty quickly, but if you're really jamming, you might proceed before these come online. So we'll just give them a second to come online here. Excellent, and now they are all online. So we'll just double check the Calico nodes, and they look excellent. And so this will require a couple configurations with YAML. The first one, we have to configure metal B, and this time we have to set the IP address range we want to do. So when we access the website, we'll actually use 11.200. So again, we'll just use sudo nano, which is just a text editor in Linux. And then we will copy our configuration. Now we apply it. And we can see they have been created. Now we need to create a namespace called ingress Nginx. And then let's make sure the pods look okay before proceeding. And so I missed a step there. We actually need to apply the deploy YAML first. So we created the ingress Nginx namespace, and now we need to apply the deploy YAML manifest. And now we should start to see the ingress Nginx pod come online. And again, before proceeding, I mean, you could get jamming and you just move too fast before this pod is created, and then you'll have issues. So we'll just want to give it a second to boot up here. Excellent, and now it is online. So there is a patch we need to do here. So we'll go ahead and patch. This has to do with the load balancer. And when we take a look, we will now see we've got our cluster IPs and our load balancer IPs, and the external IP 192.168.11.200. This is how we'll access the custom website. So this image is so small that it's not as critical, but we'll go ahead and pull it. And then we're finally ready to create our deployment manifest. Okay, so we pulled that image, the Alpine image, going back into Nano to post our configuration, and then this is how the variables or the elements in the web page are dynamic, is because I defined the variables here in the deployment file. So depending on your hardware, your OS version, you'll get different values for your CPU, the number of logical processors, depending on your environment. So it's not just a static website. It's actually pulling information when the container is created dynamically. So this will use 9 pods to get started, and then there's some other stuff going on here, like pulling the default website before we make edits. what ports to use, and mentioning the Nginx ingress, and the ingress class name is Nginx. So this is a bit lengthy, and it's almost a whole nother discipline to understand every line. So for our purposes of the AZ800, we won't go into too much detail on each section, but we'll want to copy and paste this into our YAML file, and then we will apply it. Excellent. And so we've reached a major milestone, and we will see our 12 pods start to come online in our Kubernetes cluster with Linux worker nodes. So we can see the pods are initializing. And they're up and running. One thing I've noticed in testing is these containers and pods seem to initialize a bit faster. I suspect it has something to do with the Windows platform. Maybe it's a bit more heavy on resources. Maybe the Nginx is a bit more lightweight, and so then the containers can get started much faster. So excellent. So now we will scale the deployment up to 21 pods. But first we'll just we'll do a little testing. So we'll plug in 192.168.11.200, and now the computer name is dynamically assigned. So this is whatever the container's computer name is. And so if we come over here, C5C, so that's this container. So that's the computer name, and then the script pulled the computer name and then posted it here. And you can see it's Linux. There's my Intel Core i7 and the logical processor count, and then all of the rest of the static parts of the website. And then by IP address 192.168.85.195. We'll be able to see .168.85.195. So he's on node 1. Okay, so now we will scale the deployment, and this is the best illustration of what orchestration means. So rather than us going up and standing up virtual machines, standing up containers, we just run this beautiful command that says kubectl scale deployment and how many we want. And we want 21 now. And so now it will just immediately start scaling. And I truly find it just unbelievably fascinating. So this is really neat that so we've got 3, 5, 7, 8. We have 8 gigabytes of memory right now running our virtual machines. I couldn't stand up another virtual machine if I wanted, but here I was able to stand up 21 containers to serve up a website. So the last test that we'll do, we'll just scale it up to 31. And incredible. So we've got 31 instances of Nginx. And so we'll close out by just doing a bunch of testing to confirm we are getting placed on different nodes. that there's not some issue where we're just all on the same node or something. But the master control plane node is deciding where these pods get deployed, and that is known as orchestration. So 85.205 is node 1. 58.203. So 58.203 is node 1. 58.210. 58.210 is node 2. 58.200, node 2. 85.195, node 1. And we'll just do a few more for good measure. $58,208 and node 1. So we can see that all of these containers are online, and we can determine what node they are on by their IP address. So this concludes the portion of the lab about Kubernetes clusters, and now we will just finish off with an example of nested virtualization. We'll finish off this lab with a demonstration of nested virtualization. And we actually already configured a server for nested virtualization when we did the Docker build server because we wanted to test Hyper via isolated containers. So we'll do the same process here. So on my Hyper-V host, I've created a virtual machine called mcm-nested host 01. And this is going to be the machine where we prepare for nested virtualization. So the first thing we have to do is expose the virtualization extensions. So we have to stop the virtual machine, expose the extensions, and then start the machine. Oops, I did not grab the computer name. And so now the virtualization extensions are exposed. And so now we'll install the containers role and Hyper-V. So if we had not exposed the virtualization extensions, then you get an error message there when you try to install Hyper-V. So this does take just a moment, so I'm going to pause the recording while the role gets installed on our nested Hyper-V host. Okay, so the role finished and the virtual machine rebooted. So there's one little gotcha when we start doing nested virtualization. We will want to enable MAC address spoofing on the interface that's going to be using the external switch. So from the host, we need to turn on MAC address spoofing. So now when we look at the host, we go into settings and then look at the network adapter, and in advanced features, here is MAC address spoofing. We could have just checked this box to turn it on, but that's the PowerShell way to turn on MAC address spoofing. So we'll come into our host. And so the first thing we're going to need is an external switch. And so the interface on the virtual machine on the Hyper-V host, its name is just Ethernet. And that's the only adapter that it has. So we're going to do a new VM switch, call it nested ext, and then we're using the Ethernet adapter. And there is our external Hyper-V switch, and then this is the interface. So now what I'm going to do is get the golden image from the host. So what you can do on these virtual machines, we'll come in here, we'll turn on file sharing, and then we will go to map a network drive, or excuse me, we want to add a network location. And we're going to specify our Hyper-V host. And we'll just reference the C drive. And then what happens is we'll get credentials for that computer. So we'll try it by IP address. So it just wasn't doing name resolution, so we just did it by IP address. And then we need to put in the username, so Hyper-V host LT, and then my account is Mark. Excellent. And then so it maps that C drive. So this is kind of a convenient way that we can grab the golden images and move them to the nested Hyper-V host. And so now I can take my custom functions I use to create virtual machines with and run it inside of this nested Hyper-V host. And then I'll be able to create virtual machines. So I'll create a generalized image version and a server core image. Okay, the golden images just finished transferring. I'm just going to minimize this in case we need it later. So now we're going to create our nested virtual machines. And you could use Hyper-V Manager, and you can see in Server Manager we have the Hyper-V Manager tool for our nested virtual machine. So right now there are no virtual machines, but we'll go ahead and create 2 of them. There we can see the virtual machine has been created, and then my function should start it up here. What's happening is it's taking the golden image and it's copying it to the directory that the virtual disks live in and renames it before adding it to the virtual machine. So that's what's happening right now. It's copying that golden image file and renaming it. So it does take just a second. So we'll wait for this other one to kick off, and then we'll go inside and just take a look at and do some testing. But now we've officially created a nested Hyper-V virtual machine. Excellent. So now we've officially created 2 nested Hyper-V virtual machines. So we'll just go in and take a quick look at them. And you'll notice it's a bit more sluggish than if you were to create virtual machines on the normal Hyper-V host. And that's one of the concepts from nested virtualization, is you start to lose performance the deeper you go into the nesting. So we'll try to get into the server core one. So we'll just give them a bit of time to start up here. So this is the desktop experience. And so my golden image has some standard user accounts and the background image set. So once this gets booted up, we'll see the background. The time is set to Alaska Standard Time. And we saw the 2 accounts there before logging in. Oops, I'm going to go ahead and get the server core one going. Well, we'll just pop into the desktop experience. So this is, we are inside MCM nested VM 01. So what we want to do is just show that we have access to the internet. One way we can check that is by pinging 8.8.8.8, which is Google, and the weather. Excellent. Oops, sorry, that was my loud thump. Excellent. So everything is looking good. See, we're having pretty good weather. And then we'll just check out the oops, I closed down my window. We'll check out the server core instance. Oop. So you can see it gets a bit complex when you start nesting. There we go. So now we'll check out the other virtual machine. So this one is an instance of server core. And we can see we can ping the internet. And one way we can prove what our Hyper-V host is we can use this get item property command, and we can take a look at some files in the registry to see what the host is. Let me just come back in here. I need an enhanced session. It doesn't want to give me one. So we'll have to turn on enhanced session mode. This allows us for copy and pasting. Go ahead and click apply. So now we'll see if we get the... Yes. So the enhanced in session allows me to copy and paste. It was on by default on the Hyper-V host, but the nested one was not. So that's a good one for the curriculum. It talks about where to turn on enhanced session, and I did it in Hyper-V settings. So now when we run this, we can see the get item property. We're looking at the local machine, software Microsoft virtual machine guest parameters, and it tells us what the host is. And then similarly, if we run it, well, if we just run it from the host, we'll see that it's the actual Hyper-V host that is, or the laptop is the host. And then the virtual machine is the host for the nested virtual machine. So this will conclude the containers, Kubernetes clusters, and nested Hyper-V lab. So I found the Kubernetes stuff unbelievably fascinating. I've been fascinated with virtualization ever since I created my first virtual machine about 10 years ago. And the technology is constantly advancing. So the main thing to remember with containers is the shared kernel allows them to be more efficient. So thanks for watching, and have a great day.